In our last lecture, we had commenced our study on dimensional analysis. Okay. I had defined for you dimensions and units. Okay. As I said, the measure of a quantity is called the dimension, and the standard that is used for that measure is called a unit. Okay. So, for example, in this case, the fundamental dimensions, all quantities can be expressed in terms of a set of fundamental dimensions, and there are 6 of these: mass, length, time, temperature, electrical current or amperes, and light or candela. And we had derived the dimensions of various quantities that are in common use: mechanical, thermal, as well as those that go for concentration and diffusion coefficients and so on in the last lecture. Okay. We will continue our study in this lecture and look at some more examples of how to derive dimensions. Okay. So, we had derived for you the stress, the viscosity, the flux, the thermal conductivity and so on in the last lecture, and we will examine now how to determine the dimension of some unknown quantities. Okay. So, let me solve one example for you. Okay. I told you that the relation between the stress and the strain rate is given by the stress is equal to the viscosity times the difference in velocity divided by delta z for a fluid. Okay. Now, this is valid only for a general class of fluid called a Newtonian fluid. Okay. In that case, the stress is proportional to what is called the strain rate, which is this V divided by delta z. Okay. You can have other types of fluids for which this is not true. Okay. So, for example, there exists a class of fluids which are called power law fluids, okay, for which the stress is equal to some coefficient. Okay. It is called the flow consistency index times V by delta z times the magnitude of V by delta z whole power n minus 1. Okay. N is a number, it is called the power law index, okay, and K is called the flow consistency index. Okay. So, how do we determine the dimension of this flow consistency index? Okay. We do that by substituting the dimensions on the left and the right hand sides. Okay. So, in this particular case, for example, the dimension of stress is m L inverse T power minus 2. Force per unit area, force has dimensions of ml square and T power minus force has dimensions of mass times acceleration, and you divide that by area and you get the dimension of stress. Okay. Is equal to the dimension of this index K, okay, times the dimension of V by delta z, that is L by, okay, the velocity is length per unit time, okay, divided by length, okay, times another length per unit time by length to the power of n minus 1. Okay. You can see that in this case the length dimensions both cancel out. Okay. Okay, the numerator and denominator, because you are taking velocity divided by distance. Okay. So, this is basically equal to the dimension of the flow consistency index times T power minus n. Okay. Therefore, I have to divide or multiply throughout by T power n, and I will get the dimension of the flow consistency index, m L inverse T power n minus 2. Okay. I multiply both sides by T power n. Okay. Okay. So, this is how you would get the dimension of some unknown quantity based upon a relationship involving that quantity. Okay. And I should note that this index n in general need not be an integer. Okay. It could be a fractional number as well. So, there could be quantities which have dimensions which are fractional as well. Okay. As long as they are used in equations in which the dimension is the same on both sides, the system is consistent. Okay. So, the dimension of a quantity does not have to be an integer, and in order to illustrate that I went through this example. Okay. Next, let us consider the dimensions of some electrical quantities. Okay. Okay. Current is a fundamental quantity. It has dimension ampere, okay, A. Okay. What is the dimension of voltage? Okay. You get that from a relationship which involves the voltage in which you know all other quantities. Okay. We know that the power in a circuit, okay, is equal to the current multiplied by the voltage. Okay. The dimension of power, energy per unit time, okay, m L square t power minus 3. Okay. Energy is ml square t power minus 2, okay, force into distance. Power is energy per unit time. Okay. That has to be the dimension of current times the dimension of voltage. Okay. It has to be the dimension of current times the dimension of voltage. That means that the dimension of voltage is m L square t power minus 3 A inverse. Okay. That is the dimension of voltage. Okay. What is the dimension of electrical resistance? Okay. We know that the electrical resistance, okay, is equal to voltage difference divided by current. Okay. So, therefore, the dimension of resistance okay, is going to be equal to the dimension of voltage difference m L square t power minus 3 A inverse divided by the dimension of current. Okay, that is okay. So, that is the dimension of electrical resistance. Okay. Next, let us look at the dimension of capacitance. Okay. What is the electrical capacitance? Okay. If I had a capacitor, okay, across which I put a voltage difference, okay, across which I put a voltage difference, okay, then the charge, that voltage difference is related to the charge that is stored in that capacitor by the relationship delta V, the charge is equal to capacitance times delta V. Okay. The charge stored in a capacitor is equal to the capacitance times the difference in voltage that is applied across the capacitor. What is charge? Okay. So, before I discuss capacitance, it is worth discussing what is charge. Electrical charge, I mean. The electrical charge is basically the current flowing is basically the number of charges flowing per unit time. Okay. So, current is equal to the charge that is transported, okay, that is the electrical charge. Okay. So, per unit time. Okay. Therefore, the dimension of current which is amperes A, okay, is equal to the dimension of electrical charge divided by the dimension of time. Okay, so that is the relationship. Therefore, the dimension of electrical charge is basically the current into time. Okay, so that is the dimension of charge. Okay. Now, back to our dimension of capacitance. Okay. Q is equal to C into delta V. Okay. That means the dimension of charge, which is A times T, okay, is equal to the dimension of the capacitance C times the dimension of the voltage, which is M L square T power minus 3 A inverse. Okay. So, therefore, I divide throughout by this dimension of voltage, and I will get that the dimension of capacitance is M inverse L power minus 2 T power 4 A square. Okay, that is the dimension of capacitance. Okay. Okay, so M inverse L power minus 2 T power 4 and A square. Okay, so that is the dimension of capacitance. Okay. The other quantity that is often used in electrical quantity is what is called the inductance. The capacitance was related to the charge stored, the inductance is related to the rate of change of current. Okay. Okay. If you have a steady current, then there is no voltage difference for an inductor. If the current varies with time, then the voltage difference for an inductor is delta V is equal to the inductance L times, okay, so I should not confuse it with length. Okay, so I will use this. Okay, the inductance L into the change in current divided by the change in time. Okay. That means that the dimension of voltage, that is M L square T power minus 3 A inverse, okay, is equal to the dimension of inductance into A, the dimension of current, divided by T, the dimension of time. Okay. And therefore, you can get the dimension of inductance by multiplying both sides by T and dividing by A. Okay. You multiply both sides by T and divided by A, and you will get the dimension of inductance as M L square T power minus 2 A power minus 2. Okay. Yeah. So, those are the dimensions of some common quantities that we encounter in electrical systems. Okay. And you can derive all of these starting off with a relation which involves one of these quantities and all other dimensions which are known, which are all other quantities which have known dimensions. Okay. So, that is how you determine the dimensions of all the quantities. Okay. Go to some relation which involves that particular quantity and involves other quantities, all of whose dimensions are all known. Okay. Okay. So, quantities have dimensions. Okay. As we will see later during this course, when we write down equations, okay, equations also have dimensions. Okay. So, equations also have a dimension. What that means is that all additive terms in that equations have the same dimension. Okay. So, for example, you cannot write an equation where one of the terms has dimensions of length and the other term has dimensions of time, for example. Okay. The reason is that if I change the unit of length, okay, from meters to centimeters, the term which has dimensions of length will change term with dimensions of time will not change. So, the equation is no longer valid. Okay. An equation can be valid when expressed in any units only if all additive terms in that equation have the same dimensions. And let me explain that. Okay. Many of you must have seen the Bernoulli equation. For the pressure in the fluid. Okay. Basically, what the Bernoulli equation, the way it is usually written is P plus half rho V square plus rho G H is equal to a constant. Okay. So, basically the sum of 3 terms is equal to a constant. Okay. Now, when the sum of 3 terms is equal to a constant, each of those terms has to have the same dimension. Okay. Otherwise, the equation is not dimensionally consistent. Okay. If I change units, then one term will change, another won't, and therefore, the equation is no longer valid. So, let us examine the dimension of each of these terms. Okay. Pressure we had already derived. Okay. Mass length inverse T power minus 2. Force per unit area. Okay. Force was mass times acceleration m L T power minus 2, that divided by area is this. Okay. That is the dimension of the first term, the pressure. Okay. The dimension of the second term is the dimension of density. Okay. M L power minus 3 is the density, mass per unit volume. Okay. So, okay. Times the square of the velocity. Okay. Times the velocity has dimension L by T, the whole square. Okay. So, you have m L power minus 3 multiplied by L square divided by T square. Okay. So, you can easily work this out, cancel all the common terms, and you will get m L inverse T power minus 2. Okay. And the dimension of the third term here, density times gravitational acceleration times h. Okay. M L power minus 3 is the density. Okay. Gravitational acceleration, rate of change of velocity. Okay. Length per T power minus 2. Okay. Okay. The velocity is L T inverse, and rate of change of velocity is L T power minus 2, okay, into the height h, which has dimensions of length. Okay. And you can easily work this out once again. This has dimensions of m L inverse T power minus 2. Okay. So, you can see that the dimensions of all of these terms are all the same. Okay. And that is the dimension of the equation. Okay. Therefore, the dimension of the constant on the right side also has to be the same. Okay. And this is the dimension of the equation. Okay. Okay. So, all equations will have dimensions. In this particular case, the equation is an algebraic equation, and it has dimensions of the same dimension as pressure. Okay. Because each term, each additive term in the equation has units of pressure. Okay. So, that is for ordinary algebraic equations which do not involve any derivatives. Okay. As I had said in my introductory class, okay, the equations that we will be treating will be having derivatives. Okay. Derivatives both with respect to position as well as with respect to time. Okay. And just as quantities have dimension, derivatives also have dimension. Okay. So, for example, the derivative d by dx, okay, it has a dimension which is length inverse, okay, where x is the spatial position. Okay. Similarly, d by dt, okay, time derivative has dimensions of t inverse. Okay, so, derivative with respect to time. Okay. So, what is the spatial derivative of a quantity? So, for example, if I wanted to calculate the change in concentration when I moved a small distance delta x. Okay. Okay. So, let us say that I had a domain where the concentration was varying with position, and I wanted to find out what is the change in concentration if I moved a small distance delta x in the x direction. Okay. So, the concentration will basically be delta C is equal to delta x times dC by dx. Okay. That is after all the definition of the derivative, the change in concentration when you move a small distance, okay, okay, in the limit as delta x goes to 0. Okay. Okay. So, dC by dx is equal to limit as delta x goes to 0 of delta C by delta x. Okay. So, that is the definition of the derivative. Okay. And you can see that the derivative part, okay, the derivative part has the same dimension as this 1 over delta x, okay, because the concentration, the change in concentration has the same dimension as concentration. Therefore, the derivative has the same dimension as the inverse of length, okay. That is for a spatial derivative. The time derivative has the same dimension as inverse time. Okay. So, derivatives have dimension. Okay. A derivative with respect to one particular quantity has dimension of the inverse of that quantity. Okay. Similarly, integrals also have dimension. Okay. Integral, okay, dx times f of x, okay, has the dimension of dx times the dimension of f of x. Okay. Therefore, the integral, a spatial integral, has dimensions of length, okay, because it has the dimensions of the variable over which it is being integrated, and area integral will have dimensions of length square, okay, because it is an integral over area. Volume integral has dimensions of length cubed. Okay. So, those are the dimensions of derivatives and integrals. Okay. And in differential equations you have to include the dimension of the derivatives as well. Okay. Now, later on in the course we will encounter other derivatives. Okay. One of them is, for example, called the gradient. Okay. It is denoted by this symbol. Okay. Do not worry about what it exactly means, we will see it later in the course. The limited point I would like to make here is that this has dimensions of length inverse. Okay. This has dimensions of length inverse. A square of the gradient has dimensions of L power minus 2, okay. A cube has dimensions of L power minus 3, and so on. Okay. So, even though we may not fully understand what the physical interpretation of these quantities is, that is something we will come to later in the course, but just based upon dimensional analysis we can check consistency if we know the dimension of all of these operators, the derivatives, the integrals, as well as the vector derivative operators. Okay. With that we can examine the dimension of a more complicated system. Okay. So, the Navier-Stokes equation for the momentum of a fluid, okay, is expressed as rho times partial v by partial t, v is a vector, plus v dot grad v is equal to minus grad p plus mu del square v. Okay. So, that is the momentum conservation equation. We have not yet done the meaning of these symbols, but we can just examine their dimensional consistency. Okay. To do that we have to first express it as an additive sum of multiple terms, okay, as an additive sum of multiple terms. So, I expand out this bracket and write this as rho times partial v by partial t plus rho v dot okay. Now that I have expressed it as sum of various terms, all of those terms have to have the same dimension. Okay. This dot product and the cross product and all, they are vector products, they do not have any dimension, they are dimensionless. Okay. All other terms have dimensions. So, let us examine the dimension of each of those terms. Okay. So, the first term here, density is m L power minus 3, okay, and the velocity is L t inverse, okay, and I have a time derivative. So, the derivative has dimensions of inverse time. Okay. So, the derivative has dimensions of inverse time, and I will get the net dimension of the first term as m L power minus 2 t power minus 2. Okay, that is the derivative of the first term. Okay. The derivative of the second term here. Okay. Density has dimension of m L power minus 3. Right. Velocity has dimensions of L t inverse. Okay. Dot product has no dimension. Gradient has dimensions of inverse length. It is a derivative with respect to length. So, it has dimensions of L inverse, and the velocity has dimensions of L t inverse. Okay. So, you can see that the net dimension, the net mass dimension is just m, okay, because m appears one time. Length I have minus 3 plus 1 minus 1 plus 1. Minus 3 plus 1 is minus 2 plus minus 1 is minus 3 plus 1 is minus 2. So, you will get L power minus 2, and this time dimension has t power minus 2. Okay. So, it has the same dimension. The pressure term here, okay. Grad of pressure. The gradient has dimensions of length inverse. It is a derivative with respect to length, and the pressure has dimensions of mass length inverse t power minus 2. Okay. And you can see that it has the same dimension as the other terms m L power minus 2 t power minus 2. And this last term here, viscosity, we had calculated it in the last class, m L inverse t inverse. Okay. That is the dimension of viscosity. Okay. Del square, two derivatives with respect to spatial coordinates. So, it has dimensions of length power minus 2. Okay. And velocity has dimensions of length t inverse. Okay. So, it has mass dimension to the first power. I have L power minus 2 minus 1 plus 1. So, I get L power minus 2 and t power minus 2. And you can see that in this equation all the terms have exactly the same dimension, okay, as required by dimensional consistency. Okay, as required by dimensional consistency, each of the terms in this equation has the same dimension. So, we were able to verify the dimensional consistency without necessarily knowing what the details of each of these, the detailed understanding of the meaning of each of these terms, just from the dimension of each of those terms. Okay. Okay, so we are able to verify the dimension of all of these quantities. Okay. Yeah. So, in an equation, right, all terms have to have the same dimension, derivatives have dimension, integrals have dimension. Okay. V is a vector, okay. It has 3 components. For a vector, the components all have to have the same dimension, because the component of the velocity vector can typically be written as the velocity in the x direction times the unit vector in the x direction plus the velocity in the y direction times the unit vector in the y direction plus the velocity in the z direction times the unit vector in the z direction, okay, in a 3-dimensional space, say, okay, in which I have 3 coordinates x, y and z, and the velocity is defined at some point. Okay. Okay, this underscore I will use as a notation for vector. We will come to that later in the course. Okay. Unit vectors have no dimension, they are dimensionless. Okay. They are only directions in space of unit length. Okay. They have no dimension. The components of any vector, all components of the vector have to have the same dimension. Okay. All components of a vector have to have the same dimension, and that is the dimension of the vector itself. Okay. So, for a vector, all components have to have the same dimension, that is the dimension of the vector. Okay. Unit vectors have no dimension. Okay. Okay. So, to summarize, equations have dimension. When you expand out the equation so that it is the sum of multiple terms, each of those terms in that equation has to have exactly the same dimension, and that is the dimension of the equation. Okay. Derivatives have dimension. A derivative with respect to length has dimensions of inverse length. Derivative with respect to time has dimensions of inverse time. Integrals have dimension. Integral with respect to length has dimensions of length itself. Integral with respect to time has dimensions of time itself. Okay. Gradients have dimensions of length inverse. Okay. Okay. So, with this I have completed the discussion on dimensions and units, and in the next class we will proceed to dimensional analysis. Okay. How do we use dimensional analysis in order to simplify the relationship between quantities that are known or given in the problem and quantities that we would like to find out as part of the problem. Okay. How do we make that relationship between different kinds of quantities? Okay. That we will discuss in the next lecture. Okay. I will see you then.